The last molecule we'll look at in terms of Huckel theory is benzene, our favorite aromatic molecule. Right, and when we start looking at cyclic systems, we need to remember that, if we label our carbons, 1, 2, 3, 4, 5, 6, 1 and 6 are now neighbors. So we can write out the secular determinant. It gets a lot bigger because now we have a 6 by 6 determinant, so we're adding together 6 different p orbitals. We'll get alpha minus e all along the diagonal, just like this will always be the case for all of our problems that we're looking at. 1, 2, 3, 4, 5, we need one more. We'll end up with betas right next to it, so those are all of the neighbors. And then we'll have one more beta that shows up in the corner over here, and that's this 1 and 6 interacting with each other. Everything else is 0. So 0 there, 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 zeros here, and here, and here, and here, and here, and here, and here. And this is our determinant that equals 0. Now again, we can factor out our betas and turn things into x's and do it again. We'll just look at the results. So in terms of energies, we end up with our energies. We have 6 different results because we end up with a 6-ordered polynomial. We get alpha plus 2 beta, alpha plus beta twice. So we get degenerate states here. And then we get 2 alpha minus betas, and then an alpha, sorry, not plus, an alpha minus 2 beta. So if we plot this in terms of energies, again, where this is alpha, we'll have our alpha plus 2 beta down here, alpha plus betas, 2 of those, 2 alpha minus betas, and 1 alpha plus 2 betas. And there's 6 pi electrons in a benzene molecule, and these will all go into the bonding orbitals here. And so we get quite a bit of resonance stabilization, as we expect. That this is all these electrons spreading out over the entire benzene molecule, right? Instead of being localized in these bonds, as you're familiar with, right? When we talk about aromatic molecules, we know that those electrons are not confined to a particular point on the ring. They are spread out over the entire ring. And that shows up as molecular orbitals that spread out over the entire molecule. We can also look at the wave functions that we get from here. All right, and so if we look at, for example, this lowest energy node, if I sort of draw out the benzene ring like this, what we're going to see is all of these 2p orbitals for all of our carbon atoms. For this lowest energy, they add together in phase. So these are all positive on the top, negative lobes are all on the bottom, and we end up with an orbital that's kind of, if we kind of draw a line, this represents the carbon atoms. These orbitals kind of spread out over all the top and bottom of the molecule. And what we'll see with as we go up in energy is we're again going to introduce more nodes as we go up higher in energy. So our alpha plus beta, these will have one node in them, but still form largely bonding orbitals. And as we get up to this, these will have 2 nodes and 3 nodes, right? That we see these nodes existing between our along the bonds, meaning that they are not contributing to the bonding of the molecule. But they're not electrons in those orbitals, but there are these anti-bonding orbitals that exist at higher energies that have these nodes that are present. And so this is sort of a general trend we've seen, right, with quantum mechanics in general, right? The less nodes a wave function has, the lower energy it is. The more nodes, the higher energy. And that's just a consequence of the way the math works out in terms of these types of systems. But this is even though this is a somewhat simplistic treatment, it allows us to, find these energies, show the stabilization due to these electrons all spreading out over the molecule, just as we know from, just as you learned about in organic chemistry. So this concludes chapter 10, talking about polyatomic molecules. I told you we want to get to very big molecules. And if we want to get more in depth with this, we're going to need to use computational chemistry, which is the subject of chapter 11.